In this video, I'll be discussing a statistical technique known as bootstrap resampling, which is a method that allows us to assign or measure the error in a statistic that we've computed from a sample distribution. So it allows us to compute errors on our estimators. And the beauty of bootstrap resampling is that it's a very simple technique and allows us to estimate these errors without any knowledge of the parent distribution from which our samples are drawn. So imagine we have some sort of parent distribution, which I've denoted here as f, and we take from that distribution sort of n observations or n samples. You can imagine we have sort of x1, let's say is 2, x2 here is maybe 5, x3 is 7, x4 is 7 again, all the way down to xn. So what we end up with is a vector of sort of n observations, x1 all the way out to xn. And from this distribution, the sample distribution that we have of our observations, our n observations, we would like to know the a certain statistic or an estimator, which I'll denote here as theta hat, which is just found by applying some function s to our vector of observations. And s here could be the mean of x, it could be the median, maybe the standard deviation, it could be, or it could be something much more complex. It's sort of very generic. And we would like to know how theta hat compares to the true value of theta. So we'd like to get an estimate of the error that we've made in our estimating the true value of theta. And the beauty of bootstrap resampling is that it allows you to do that if each of these x's that we have are drawn from identical parent distributions and they're all independent of each other, then we can do this, we can compute this error via bootstrap resampling. So we compute a bootstrap sample, which I'll denote as x star, which we compute via sampling from the original vector x, but we do that with replacement. So we choose, say, randomly. First we get, say, x4, then we get x1, then we get x3, maybe we get x1 again. So we sample with replacement, so we can get the same values more than once, all the way out to sort of to x to some xn. So this is of length n vector. So I'll denote this as the first. This is the first bootstrap resample we've done. And then from this bootstrap resample, we can do the same estimator and compute s of x1 star and this provides a different estimate of our true value theta, or the true value of the estimator. So I'll call this x. This is now theta hat 1 star. And we don't want to do this just once, but we want to do this a a lot of times in order to build up a distribution of our theta hats, or a distribution of our estimators. And from that distribution of our estimators, we can compute, we can get a measure of the variability or the error. The width of that distribution will tell us something about the typical error that we've made in measuring theta hat. So we start with our data vector here, which is a length n samples, and we create B bootstrap resamples, where B is going to be something like, for accuracy's sake, 1,000 or maybe 10,000. So it's going to be a very large number in order to reduce the error in our random error in our calculations. So we create B bootstrap samples, denoted here as X star, and each of these X stars were chosen or were computed by sampling with replacement from our original array, our sample vector, such that we could get the same sample value in a given array more than once. And from our 10,000 or 1,000 statistics that we've computed from our bootstrap samples, we now get we can plot a histogram of those samples. And if n is large, where n was the original length of our samples, then we'll get something that looks very Gaussian, just by the central limit theorem. And we have some mean and some width here. And we can compute this width just as the standard deviation of this set of S, this set of statistics that we computed from our bootstrap samples. And if we say that this resampled distribution of our estimators is centered at this S bar here, then we can compute the width of our distribution just via the standard variance formula, where we compute the squares of the residuals of each of our resampled statistics. And this is a very powerful technique, because we've assessed the sort of properties of our underlying parent distribution without actually knowing using knowing the shape of that parent distribution. So it's a technique that's very advantageous when the theoretical distribution from which we draw our samples is complicated or unknown or cannot be computed analytically. And it's worth mentioning that in the case of small n, we could end up with a distribution that looks remarkably non-Gaussian. So we could have some sort of tail like this. And in that case, the statistic that we've computed, this sigma boot, this bootstrap error, doesn't have the normal sort of standard deviation of a normal or Gaussian distribution, doesn't have the same connotation. So in the case that n is small, if you want to find, say, a confidence interval, say the 95% confidence interval on your original estimator, what you will want to do is not compute the probability distribution, but this is the probability distribution. You would want to compute the resampled cumulative distribution. So you could plot the the CDF, the cumulative distribution function, which might look something like this, where it goes up to 1 here. And from that you can say, if you want to know the let's say 90% confidence interval, you could find the values where let's say 5% are greater than this value and 5% are greater than down there, and then 5% are up here. So what you can end up doing is establish those same sort of confidence intervals, but by using the resampled cumulative distribution function and not the probability distribution. But in the case of large N, your sigma, your 1 sigma error, which is the 68.3% confidence interval for a Gaussian distribution, will agree with this percentage interval that you've computed from the CDF. And lastly, you might be wondering what the value of B, the number of Bootstrap resamples you need to use in order to minimize the error in our estimate of sigma boot here. And it turns out you can show that the variance in our error estimate has terms that are proportional to 1 over n squared, where n squared, or n here is the length of our original sample array. So this is due to sampling variance. And the second term that contributes is 1 over n times b, where this is due to the resampling error. So you can see that in the small n limit, we measure a noisy estimate of the error on our original statistic, just because we've sampled the parent distribution poorly. Because n is small, we can't recreate the parent distribution well. And the second reason that we can have error in our sigma boot, in our bootstrap sigma, is that we just random error due to not enough resampling bootstrap sample distributions. And typically what is done is B is something like 1,000 or 10,000 to 10,000 in order to reduce this second term in the variance. But really, B should be just the largest possible value it can be, given time constraints and computing power for any individual case. So this really shows that with the advent of computing, we can compute an estimate of the error and confidence intervals for a statistic using no knowledge of the theoretical or analytical parent distribution that our samples were drawn from, just by using this resampling with replacement technique.